I literally just recorded this whole thing without recording my screen, so I'm doing it again. Take two. In this video, I'm talking to you about complex power. If you want a qualitative understanding of this, you can go and watch my Dr. McFerrin Explains Complex Power video. You can see the card up there right now. But what I want to do is kind of give you a brief introduction to complex power, help you understand it so that way you'd be well equipped to launch into a power course where this might be the very first thing that we talk about. So to talk about complex power, I'm going to start with what's called the power triangle. It's a fun name. It's a right triangle with a value Q over here on the right hand side, a value P on the horizontal one, and then S phasor is on the hypotenuse, and then phi, not theta, phi is the angle. So S phasor is P plus J Q. Okay, so as a vector, I can get to the same spot. It's really a magnitude with an angle. This is a triangle on the complex plane. And S phasor is what I call the complex power. It's measured in volt amperes. The magnitude of S phasor is just S, and it's what I call the apparent power. It's also measured in volt amperes. The reason it's volt amperes, watts is just voltage times current. When I start working with complex power, I want to distinguish between real power and complex power. So P is my real or average power. It's measured in watts. And then Q, which is my purely reactive power, is volt amperes reactive. That's how it's measured. Phi is what I call the power factor angle. And the cosine of phi is what I call the power factor. The power factor angle is theta V minus theta I. Let's hold on for just 1 minute and talk about how I interpret that. If phi is greater than 0, that means theta V is bigger than theta I. And it also means that I'm inductive or lagging. All right, because it corresponds to having a positive J, which is an inductive piece. If phi is less than 0, then theta V is less than theta I. And this is what I call capacitive or leading. Very easy to read there. Now, let's talk about how I actually calculate these things. S phasor is V RMS I RMS angle theta V minus theta I. Let's pause for a minute. I know V RMS is just going to be my peak over the square root of 2 because I'm working with sinusoids here. And I RMS is just I m over the square root of 2. So I could also write S as Vm Im over 2 angle theta V minus theta I. The magnitude of S phasor, S, my apparent power, is Vm Im over 2, or V RMS I RMS. Reminding you that's measured in volt amperes. I can also write it as the square root of P squared plus Q squared. Let's go back to P, my real power. P is just the apparent power, S, that's the magnitude of complex power, times the cosine of phi, or in other words, it's Vm Im over 2 times the cosine of theta v minus theta I. This should be consistent with the definition we've seen in earlier videos. And then Q is just S times the sine of phi, or in other words, Vm Im over 2 sine of theta v minus theta I. Power measured in watts, Q reactive power measured in volt ampere reactive vars. All right, at this point, I think it's a good place to stop. You at least have the equations and you could use them to do some form of problem. And so at that point, I'd say, hey, this is the last video that we have for this AC circuits series. I hope you enjoyed them. Thanks for watching.